Welcome to our channel. Watch the video to the end, like it, and subscribe to the channel to support us. Rosetta was the first probe in history to enter orbit around the nucleus of a comet, and its small lander Philae even touched that nucleus, becoming the first human-made object to land on a comet. Despite numerous difficulties and unforeseen events, the Rosetta mission is one of the greatest space epics in history and was also one of the first major challenges for the European Space Agency. Even today, 10 years after reaching its comet, Rosetta continues to produce highly significant scientific results. Rosetta extensively explored Comet 67P, Churyumov-Gerasimenko, and this encounter has unveiled some of the many mysteries that still shrouded these incredible planetary bodies that are comets. Rosetta's journey has provided us access to information that comes directly from the origin of the solar system, and this is its story. In 1986, Halley's Comet passed through the sky. It was one of the most followed astronomical events ever. Millions of people looked up to admire its beautiful tail among the stars. Halley has always been one of the most important comets for humanity and the history of science, and its first passage in the space age was an opportunity not to be missed. Thus, a real fleet of space probes, the so-called Halley Armada, was launched toward the comet, including the Soviet Vega 1 and Vega 2, NASA's International Comet Explorer, the Japanese Susei and Sakigaki, and especially the European probe Giotto. Giotto was indeed the jewel of the Armada and provided us with invaluable scientific information about the comet. These data led, as always in science, to new questions. For example, how does the activity of comets occur in detail as they approach the Sun? What is the internal structure of comets like? What is the percentage of ice compared to rock? What role do comets play in the formation of the planetary system? These and many other questions awaited answers. Thus, ESA and NASA began to develop new space probes directed towards comets to answer these questions and delve deeper into the study of comets. This led to the creation of two mission projects: NASA's Comet Rendezvous Asteroid Flyby and ESA's Comet Nucleus Sample Return. However, due to budget issues, NASA canceled its mission, and ESA was forced to downsize theirs, eliminating the sample return component. Thus, in 1993, the Rosetta project began. Rosetta, like the Rosetta Stone, the famous tablet that presents a text in the hieroglyphics of ancient Egyptian language and in comparison, the same text in ancient Greek, was a key element in deciphering the Egyptian language. Thanks to it, we were able to interpret many other texts from one of the greatest civilizations of antiquity. Similarly, the Rosetta probe would allow us to understand more deeply the comets, those planetary bodies that for millennia had been a mystery. Today we know that comets are like messengers coming from afar, both in time and space, to tell us stories about the planetary system we live in. Rosetta would become the first and, so far, the only mission in history to enter orbit around one of these objects, 67P, Churyumov-Gerasimenko. In 1969, astronomer Svetlana Ivanovna Gerasimenko participated in an expedition at the Alma-Ata Observatory in Kazakhstan. The objective of the expedition was to search for new comets and photograph some already known ones. Among these was Comet 32P, Comet-Sola. A few weeks later, Ukrainian astronomer Klim Ivanovich Churyumov was studying some of the plates depicting this comet and, at one point, noticed another unexpected comet on the edge of one of the plates. This would go down in history as Comet 67P, Churyumov-Gerasimenko, the 67th periodic comet ever discovered. Hence the letter P in its name. In fact, it takes just 6.5 years to complete an orbit around the Sun, and at the farthest point of its orbit, it reaches less than 6 astronomical units from our star, and its orbit is inclined by just 4 degrees compared to the plane on which Earth orbits. These characteristics place it in the so-called Jupiter family, those comets that have an orbital period similar to that of the gas giant. The 67P was therefore neither too far away, too fast, nor too inclined. These characteristics are optimal for reaching the comet with a space probe, which is why 67P became the target of the Rosetta mission. Initially, the chosen comet was 46P, or Tannin, but a delay in the schedule for preparing the mission caused us to miss the right moment to reach it and thus change the target. Rosetta would enter orbit around the nucleus of the comet and would even launch a small lander, Philae, onto its surface. This would be the first landing in history of a probe on a comet. Rosetta was launched in March 2004 towards 67P, using the gravitational slingshots of 3 Earth flybys and 1 Mars flyby to get onto the right trajectory to reach the comet. To get there, it crossed the main asteroid belt, and along the way, it took a look at asteroids 2867 Steins and 21 Lutetia. Then, in 2011, it entered a hibernation phase to conserve energy while waiting to approach the comet, as energy was a precious resource. Rosetta was the first mission to rely solely on solar panels for energy production beyond the main asteroid belt. 3 years later, in January 2014, Rosetta finally came out of hibernation. It was still a great distance from the comet, about 9 million kilometers. The encounter with 67P would take place a few months later, in August, after a long phase of preparation and calibration of scientific instruments. Rosetta was equipped with 11 scientific instruments, 6 for studying the nucleus, 1 a package of instruments for studying interaction with solar winds, and the remaining 4 for studying the gas and dust in the comet's coma. Specifically, there were spectrometers used to break down light at different frequencies and thus study the mineralogical and chemical composition of the comet. The ALICE spectrometer worked in ultraviolet, while VIRTIS operated both in infrared and at visible frequencies. OSIRIS was Rosetta's camera, capable of obtaining both images and spectroscopic data in the visible and infrared. The MIRO instrument was able to observe at microwave frequencies, primarily to study the abundance and temperature of water, ammonia, and carbon dioxide. CONSORT was a radar for studying the internal structure of the nucleus, while RSI used the antenna to calculate the mass of the nucleus and the physical characteristics of the coma. ROSINA studied the composition of particles in orbit near the comet. MIDAS was used to study the characteristics of the dust collected on a silicone plate, while COSIMA measured its composition. JADA studied the dynamic properties of the dust, such as speed and size, and finally, RPC was used for the study of the interaction between solar winds and the comet's coma through various scientific instruments capable of measuring plasma, charged particles, and the magnetic field. In the first 2 months of the mission, the probe studied and mapped the nucleus of the comet. Its main goal during this phase was to choose the most suitable landing site for Philae. Indeed, Philae was a passive lander. Rosetta would launch it onto the comet's nucleus, but it could not move autonomously in any way. Therefore, extreme care was taken in selecting the landing site. This location had to allow Philae to descend safely and also to carry out an initial phase of scientific measurements where each instrument would be activated at least once. From the surface of the comet, it would thus obtain its first scientific measurements. The comet's distance from the Sun during this measurement phase was 3 astronomical units. A subsequent measurement phase for Philae would instead occur as the comet moved from 3 to 2 astronomical units. The site had to be chosen in such a way as to ensure at least partial illumination of the solar panels in both of these phases. The panels would need to provide energy to Philae's 10 scientific instruments. Thus, the site of Aegylkia was chosen, which seemed to meet these criteria. On November 12, 2014, Rosetta released its small lander. The release of Philae occurred nominally. The velocity was correct, the lander's legs deployed, and the uncertainty about the landing site was 500 meters. The lander would arrive very slowly, at a speed of 1 meter per second, taking a total of 6 hours and 59 minutes for the entire maneuver. It would slow down and correct its trajectory with a small thruster, the active descent system, which was supposed to guide the lander during the descent phase. Then, once close to the comet, it would fire 2 harpoons to anchor to the surface. At 15:34 on that day, Philae touched down at Aegylkia, just 112 meters away from the preset point, thus becoming the first human-made object in history to touch the surface of a comet. But then problems arose. Before touching down, the gas container for operating the active descent system had not opened. Philae could only rely on the 2 anchor harpoons. However, for reasons still unknown, these also failed to function. Philae then fell onto the surface, sank slightly but then bounced. The gravity on a comet is low, and without an anchoring system, it's really difficult to stop. Thus, Philae spun around the comet for about 2 hours. However, not everything was lost. During this entire phase, many of Philae's scientific instruments remained active, thus allowing it to collect data and send it back to Rosetta. After 1 or 2 bounces on the comet, at 1731, Philae finally found its long-awaited rest in the region known as Abydos. For more than 2 days, a total of 56 hours, it continued to send data. The scientific observation program was adjusted on the fly to manage the new situation. The data from the lander were then received and proved to be invaluable. However, Philae was supposed to collect data for 3 months, but the landing site at Abydos was shadowed and sunlight was too scarce for the solar panels to perform their function. Thus, in the early minutes of November 15, as soon as the batteries ran out, Philae entered a hibernation phase and we thus lost contact with the small lander. Months later, in June 2015, the sun briefly illuminated the panels again and Philae managed to send a last data packet to Rosetta about the status of its instruments, but it was a swan song because, after that last transmission, it remained silent forever. Meanwhile, Rosetta continued to observe Comet 67P. It did so for years, allowing us to obtain a wealth of valuable data about the comet that added to the few obtained by Philae during the 56 hours it was operational. The lander and the probe were able to observe the comet in tandem, providing the unique opportunity of simultaneous observations of the same object, something that is very rare in space. For example, the probe measured a magnetic field while Philae discovered that there is no magnetic field on the nucleus, which means that the magnetic field was only present in the coma and therefore had to be related to the interaction between the solar winds and the gas expelled by the comet. Comet 67P, Churyumov-Gerasimenko, is approximately 4 by 4 kilometers in size, but its mass is divided into 2 lobes. One is 4 kilometers and the other 2.5 kilometers, connected through a narrow neck. This is what astronomers call a contact binary body, similar to many other asteroids and comets we have observed. The 2 lobes were perhaps separate at one time and joined through a gentle collision that occurred at the origin of the solar system. When the probe arrived in orbit near the comet in 2014, it was about 4.3 astronomical units away from the Sun. Already from there, at a distance similar to that of Jupiter from the Sun, the comet was beginning to activate, emitting dust and also some water, and its coma was being swept by solar winds. The 2 tails of the comet were forming, one of dust and one of ions. For the release of Philae, Rosetta had approached the comet to a distance of only 10 kilometers from the nucleus. However, due to the increasing comet activity, it had to move further away. In March 2015, the dust expelled by the comet became so much that it caused navigation problems. The probe thus entered an emergency state and the mission team was forced to move it away from the dust, bringing it to an altitude of 400 kilometers above the comet. Moreover, all subsequent orbits were modified to find a compromise between proximity to the nucleus and dust density. The activity reached its peak around perihelion, the point in the comet's orbit closest to the Sun. There, the surface of the comet showed the largest changes. Rosetta observed landslides and increasing dust intensity, boulders moved on the surface, intense jets of gas escaped from the crust, and the cracks on the surface of the nucleus increased in size. There were many boulders. Rosetta counted 3,546 larger than 7 meters. These would have likely formed through comet activity, capable of fragmenting and splitting the rock of the nucleus. Rosetta's observations also finally answered a question: are there more ice or more rocks in comets? One of the prevailing models until the 1990s regarding the composition of comets was Whipple's model, which envisioned comets as dirty snowballs, i.e., blocks of ice with a small fraction of dust and rock. Observations by Rosetta, however, showed the exact opposite. Comets are primarily made of rock enriched with ices and volatiles. In 67P, there were 3 times more rock than ice. Moreover, Philae had established that the nucleus of the comet was extremely dry, very dark, and rich in organic material. At the time of the encounter, the comet reflected just 6% of the sunlight and its surface contained less than 1% water ice. Regarding organic material, Rosetta and Philae found 16 different types of organic molecules on the comet. Among these was an amino acid, glycine, along with some precursors like methylamine and ethylamine. These findings are extremely significant in terms of the origin of life on Earth and elsewhere in the universe. The composition of the water on 67P was different from that on Earth. Water on Earth is a mixture of molecules containing hydrogen and others that contain deuterium, an isotope of hydrogen with a proton and a neutron in the nucleus. The deuterium on the comet was 3 times more than that on Earth. This has significant implications for models of the origin of Earth's water. It suggests that water on Earth could not have originated solely from comet impacts because the temperature in this part of the solar system was too high at the beginning of the solar system's formation. Therefore, one hypothesis is that water was delivered over billions of years through the impacts of asteroids and comets. But if the water composition is so different, it means that comets similar to 67P could not have been the main contributors to Earth's water. These were just a few insights from the many results of the Rosetta mission. Rosetta and the ill-fated Philae have indeed obtained a vast amount of data, so much so that they will continue to produce scientific results for years, if not decades. The final phase of the Rosetta mission took place between August and September 2016. During this phase, the probe drew ever closer to the comet. On September 2, it even managed to snap a last photo of Philae, which until then had remained abandoned, shrouded in darkness. Then the probe continued to approach, obtaining data with a level of detail never reached before. Finally, on September 30, Rosetta made a controlled impact on the comet, thereby ending its mission. Thank you for watching. Leave a comment and subscribe to the channel to support us.